All right. Last time we talked about kinetic friction, which, as you know, is friction between two objects when they are sliding past each other. So static friction was the friction when two objects were stationary and keeping in place. Now kinetic friction is the friction where we're moving past each other. We already talked about the fact that kinetic friction equation looks really, really, really similar to the static friction one, except for the fact that kinetic friction has one value instead of a series of values like static friction had. All right. Knowing this, we're going to go ahead and do an example problem. Okay. We're still dealing with the same book that we talked about before. All right. It's that 0.54 kilogram book. And it's sitting on Earth. All right, so those parts of my diagram are the same. But now we're looking at something a little bit different. We are still pushing our book. So we still have the force of push. And we are still having friction impede or get in the way of its motion. So we do have friction opposite that. But now we are dealing with kinetic friction since our object is moving. What do you notice is the difference between the value of the force of push here versus the force of push we saw in the last problem? Not on an incline. We're still on a flat surface. Compare this value to the value we saw before. 3.2 is bigger than 4.1? It's smaller. All right? So once you get your object moving, it takes actually a lot less force to keep it moving, right, than to get it started. Okay, so we are going to see the fact that the coefficient of kinetic friction is going to be smaller than the coefficient of static friction was. And that's generally true in most cases. And that does have to do with the inertia of an object. An object's tendency to stay at rest, an object's tendency to stay in motion. So we are going to go ahead and look at the magnitude and direction of the kinetic friction if you push the book with a force of 3.2 newtons. When we look at this, when you're trying to look for a force, and you have your diagram, what's the first thing that you do? Yep, so we apply Newton's second law. The sum of my forces is equal to the mass of my object times the acceleration. Now the frictional force, is that going to be in the y direction or the x direction? X. So I'm looking at the sum of the forces in the x direction is equal to the mass times the acceleration in the x direction. All right. If my object is moving at a constant speed, hold on. The recording stopped. Now we've fixed that technical question. Force of which one? The one up here? Yeah. That's the kinetic friction. Yep. So the thing I was actually trying to get to is if you have a constant speed, what is your acceleration? 0. If you have a constant speed, your speed is not changing, in which case your acceleration is 0. So my right-hand side of my equation goes to 0. When I add my forces, you do need to take a look at what your sort of coordinates are set up. All right? I'm going to go ahead and set them up the same way I did the last problem. My up is positive y, my to the right is my positive x. In which case, my sum of my forces is going to end up being my force of push minus my frictional force. Right? My force of push is positive because it's in the positive direction. My frictional force is going to be negative because it's in the negative direction. Right. That actually tells me that my frictional force is going to be equal to my force of push, right? Because when you rearrange that, So as a result, my frictional force is going to be 3.2 newtons opposite your push. Oops, helps if I can figure out how to spell the word push. Are there any issues, comments, questions, or concerns at this point about what is the value of the kinetic friction on the actual book? None. All right. Thank you. I was enjoying the head shake. That's fine. All right. So, all right. Now we're going to go ahead and look at what's going on for the normal force. The normal force is in our vertical direction. So now we're going to apply Newton's second law in the vertical. So we're looking at the sum of my forces in the y direction is equal to the mass times my acceleration in the y direction. Do we have any y acceleration? No. So the right-hand side of my equation, again, is 0. So my sum of my forces in the y direction is equal to 0. We're on a flat level surface, right? So we get our normal force minus our weight, ends up telling us that our normal force is equal in this case to our weight. And as we know, weight is equal to mass times gravity. When we do that math, we do get the fact that my normal force is equal to the 0.54 kilograms times 9.8 meters per second squared. And what is the value of my normal force? Do we have some agreement? It's 5.3, 5.1? 5.3. 5.3, okay. And what's our unit there? What's our unit?
Newtons.
Newtons, there we go. It is a force. All right, so we have the value of our frictional force. We have our value of our normal force. Now we're ready to go ahead and start talking about what is the coefficient of friction. We know from our formula that we discovered, we're given, all right, the fact that friction is equal to the coefficient of friction times the normal force. Well, hot diggity darn, we got 2 out of the 3 of those items, leaving us with the thing that we actually want. We rearrange the equation, we get the coefficient of friction is equal to our frictional force divided by our normal force. Right? We're given both of those values. So we can go ahead and just sort of plug those in. Right, so what's that value?
0.60.
Right, is there a unit attached to that? Nope, right, because I do have newtons over newtons, they do cancel. So that is my coefficient of kinetic friction. Does anyone remember what the coefficient of static friction was? Look back in your notes. 0.8, right? So notice the static friction was 0.8, but our kinetic friction was 0.6. So we do see that value being smaller. Any questions about example 2? We're good? Is anyone still copying? We're going to talk about rolling friction. We're not going to go too deep into rolling friction. Rolling friction is going to matter when we get to rotational motion in January, and we talk about torque. Until we talk about torque, this doesn't really make much sense. We do need to look at the fact that rolling friction happens when an object rolls without slipping. So the bottom of the tire is sort of in contact with the ground until the next piece of tire is in contact with the ground. Right? This is a very, very specific type of friction. All right? Would rolling friction be considered static or kinetic? No, static, because you do want that piece to be stationary, right? If we see any sliding, we're not going to have true rolling friction. All right, so you do need to have sort of static friction right happening there. No, I'm not bringing the cats to class. All right, so we're going to go ahead and do another example problem. We're going to look at the fact that we're forced to stop our car. Your tires lock up so they do not roll, but the rubber slides across the asphalt. Initially traveling at 6.8 meters per second to the right, which is positive. How far do you slide before coming to a stop? And we're given the coefficient of friction for rubber on concrete. So if I were to go ahead and draw this picture, I have my car. It has a weight down, a normal force up, and it's traveling to the right, but friction's bringing it to a stop. So which direction is friction acting in?
Left.
To the left.
It's a cool car you drew.
Thank you. I'm very proud of my cars.
What's right?
All right. So we are going to look at several different pieces of information. Okay. We're trying to find out how far the car actually slides. When you're dealing with how far the car actually slides, we're going to need to deal with kinematic equations. I will tell you we don't have time, so that tells us that we need to go ahead and use the Vx squared is equal to Vx naught squared plus 2a delta x, because we're specifically looking for that delta x. We have our initial velocity. That's that 6.8 meters per second. We know our final velocity because it's coming to a stop. Right? What we don't have in this particular case is our acceleration. So that's where we now need to go to dynamics to find out what is the acceleration of our vehicle. Right? I think someone has discovered the flaw in this question. No? You look like you discovered the flaw in this question. There's a flaw. And we're going to discover it in just a second. So you'll get one more piece of information before we get any further. When we do this question, we look at the fact that the sum of the forces in the x direction is equal to the mass of my car times the acceleration in the x direction. My car is accelerating in the negative direction, so what happens to the right-hand side of my equation?
0.
It's accelerating in the negative direction, so it's going to become negative. All right?
Did you restart the recording? That needs to sound smart.
What is the only force acting in the x direction? It's the friction. All right? And is it acting in the positive direction or the negative direction? The negative.
Sort of.
All right? So, because the frictional force is acting in the negative direction and the acceleration is in the negative direction, I have negatives on both sides of my equation. What happens? They cancel out. So we can go ahead and say the fact that my frictional force is equal to the mass times my acceleration in the x direction. We're using this to find the acceleration in the x direction, right? So when I rearrange this equation, my acceleration in the x direction is equal to my frictional force divided by my mass. Right? Are we given the frictional force?
No.
No. We are not given the frictional force. We're given the coefficient of friction. So now we're going to substitute in the equation for frictional force. We know the equation for frictional force is equal to mu k times n. Do we know our normal force yet? No. So we need to go ahead and apply some of the Newton's second law in the y direction. So when I do that, we know the car's on a flat level road, so we have no acceleration in the y direction. That term is 0. My only forces acting on it are my normal force and my weight. So my normal force in this particular instance is our weight. So my normal force is equal to m times g. Now I can use this information and plug it back into my acceleration equation. When I do that, I get the fact that my acceleration in the x direction is equal to mu k times mg divided by m, just divided by m. There we go. That was. What gets to cancel? M. Right? If you jump too far ahead, you saw that we were missing the mass of the car. Did the mass of the car end up mattering? No. All we really needed was the fact that we had the coefficient of friction for the rubber on concrete. Right? Now that we have that information, we can solve our other equation for our displacement, our distance. Remember, our final velocity is 0. Our initial velocity is given to us, and we're looking for delta x. When we rearrange that equation, my delta x is equal to negative vx naught squared over 2a. Right? Our a is our mu k times g. So delta x is equal to negative vx naught squared divided by 2 mu k g. Oops, squared the wrong thing. Right. Just remember your acceleration is negative. We got that from our diagram. Our diagram said that our acceleration was negative, so that term is negative. Negative over negative cancels. So we do get a positive delta x. Someone got a solution for me? I don't know where my calculator went. Abby, what'd you get? 2.9. Perfect. All right, so you will slide 2.9 meters before you come to a stop. What if I doubled my speed? By how much more would my distance increase?
4.
By 4. Yep. Because that v squared term, if I double the speed, I will now have a stopping distance 4 times larger. How do we feel about this question?
Easy.
Easy. All right, one last problem. We're going to look at some college students borrow some cafeteria trays to slide down a muddy hill. They get a running start, so their initial speed is 4 meters per second, and the hill slope is 18 degrees from the horizontal. We want to know their speed after they've traveled 15 meters if the coefficient of kinetic friction is 0.12. So that means we're dealing with stuff on an incline now. And remember, I don't draw my angles to scale because I'm kind of sort of exaggerating what that looks like for you. Excuse me.
Bless you.
All right. Which direction is friction acting on our sledders? It's going to be 18 degrees, but it's going to be up the hill because it's the opposite direction of motion. So it's going to be parallel to our surface, up the hill, because our velocity is downward. Yep, friction is always parallel to the surface, whereas normal force is always perpendicular to the surface. So that means friction and normal force are always perpendicular to each other. We are going to set up our axes in this particular case to be tilted like we talked about on ramps before. So we are going to see our y-axis to be straight up, perpendicular to my surface, and we are going to see our x-axis going to be parallel to our surface. In this particular case, I'm going to put positive direction down in the direction of motion. Right? You can do it in the other direction. I'm just not going to. I'm going to do it this way. Right? Because of this, what do we need to do to the force of weight? Because force of weight is in both the x and the y dimension. Yep, we are going to break the force of weight down into components. Right. If I go ahead and take just that piece and blow it up, so you guys can see it a little bit better. I have my force of weight y, force of weight x. This angle in here is theta. So my force of weight y is my adjacent side in this particular case. So I do see the fact that force of weight in the y direction is equal to force of weight times cosine of theta, and force of weight in the x is going to be the force of weight times sine of theta. We've done this particular trig rearranging several times, so I went ahead and skipped some steps so that we can see the fact that my force of weight in the y direction is going to come from cosine, the force of weight in the x direction is going to come from sine.
And the theta equals 18 degrees, right? Because those are the same angle.
Correct. Due to a long, complicated geometry proof that I will not go through, that you are more than welcome to look up on the internet, this 18 degrees here is the same 18 degrees here. So we're looking at what is the speed. We're looking for their final speed. Right? We're given our initial speed. Right? We're given our delta x. We're given mu sub k. What are we missing to find what we need here? Acceleration. We're missing acceleration, right? Because that would rely on the equation we just used, that Vx squared is equal to Vx naught squared plus 2a delta x. We're missing a in order to solve for Vx squared, Vx. Right? So we are going to use our forces to find that acceleration. Right? Which direction do you think our person on this tray is going to accelerate? Up the hill or down the hill? Are they going to slow down or speed up? Is actually the better question.
Yeah.
They're probably going to speed up. So we're going to go ahead and assume our acceleration is down the hill. Assuming our acceleration is down the hill, and that's what we're looking for, do we want to go ahead and start the x direction, or do we want to jump to the y direction first? We're going to end up having to do both.
X.
We're going to do x. All right. Sum of forces in the x direction is equal to the mass times the acceleration in the x direction. Our acceleration in the x direction we already established to be in the positive direction according to the coordinates we set up, so we get to leave the right-hand side alone. The left-hand side is now going to be taking place with the x component of our weight and our friction. Because remember, we do have some of our weight, which is down in the direction of our hill. Right? So my force of weight in the x direction minus my friction is equal to the mass of my object times my acceleration in the x direction. I replace the sum of forces in the x direction with the weight in the x minus my friction, because what's pulling my block down the hill is the weight that's in that direction. And then friction is sort of keeping it from being as fast as it could be.
So it's an E.
Yeah. Yep. Right. So weight in the x direction, remember, is Fw sine theta. All right. Fw is also known as what?
Force of the weight.
Force of weight, which we could replace with mass times gravity. Okay? Sort of taking a look at this, we can already see we're running into a problem to solve this. We need the force of friction. We need to know what that value is in order to get any further to find that acceleration. Maybe. I'm seeing a couple glazed over faces. You trust, you're going to trust me? Okay. So in order to find out what that force of friction is, we know that we're going to end up having to replace that with mu times n. Right? But we don't know n. We know how to find n. That's coming from the sum of the forces in the y direction. When I do the sum of forces in the y direction, we don't have any acceleration in the y direction. Perpendicular to our surface, we don't see any acceleration. We're not moving up and down. We're just moving across the surface. So this term is 0. As a result, when I do the normal force minus the force of weight in the y direction, I do see the fact that my normal force is equal to the force of weight in the y direction, or mg times cosine of theta. Did I skip too much algebra for anybody? You want me to go back and show you? Okay. I'll take a step back. So we know the acceleration is 0. The right-hand side turns to 0. The left-hand side we're going to replace with the forces that we're actually adding in the y direction. The forces in the y direction, according to the diagram I set up, is my normal force up and my force of weight in the y direction down. So my normal force minus Fwy. That tells me that my normal force is equal to my force of weight in the y direction. We saw, when I broke my force of weight into its x and y components, that a force of weight in the y direction is equal to that weight times cosine of theta. I'm going to go ahead and substitute weight is mg, so mg cosine of theta. Okay. Now, we get to plug this back into the other equation. Because we're going to plug this in for normal force right there. When we do that, I get mg sine theta minus mu times mg cosine theta is equal to m times a. It's a process. You're going to see this equation a lot. All right, so you'll get used to this same process regardless of the other constraints on the problem. Okay, what do you notice is in every single term? Mass. So what happens to those masses? They cancel. That mass goes away, that mass goes away, that mass goes away. Right. So my acceleration is equal to all of that. I'm going to simplify it with one more step just to make that's how my brain functions. So my acceleration ends up looking like g times sine theta minus mu cosine theta. Right. Like I said, this is an acceleration you will see a lot if you're on an incline and there is friction. Right? Because remember, when we were on an incline and there was no friction, the acceleration was equal to g sine theta. When you add friction, you add this term. Right? right? That's a similar process that you see all the time. Now we have all that, we can find what is the acceleration of our object, of our car that's trying to come to a stop. Let's go ahead and plug that in so we can get a number, and then we can put that into our other equation to find our final speed. What's our acceleration? Yes, I did mean 18 degrees, not 15. Andrew, quit it.
That wasn't even me, yo.
Yeah, but you started it.
No, I did not. You're the one who left the sink on.
All right, so now that we have the acceleration, we can go ahead and find out what the final speed is. We have all of the other information, so our final speed ends up looking like, I'm going to use green, Vx is going to equal the square root of our initial speed, which was the 4 meters per second. And that term is squared, plus 2 times our acceleration, which was the 1.91 meters per second squared, times our change in distance, which was 15 meters. .4. So Abby, what'd you get? Oh, sorry.
73.
Yeah. 8.5.
Yes. Yeah, 8.5. If you kept all your digits before, it ends up being 8.56. You used the rounded number I gave you, which is fine. All right. And that is the last problem.
Same time.